Hello everyone. For last several weeks, we have covered advanced static analysis techniques for real-world applications. Okay. From this lecture, we are going to talk about some new waves in programming language-based security, especially combination with AI, artificial intelligence. Okay. Today's topic is how to overcome some fundamental limitation of conventional static analysis with AI. Okay, let's get started. Many security vulnerabilities happen because of incorrect programs caused by several reasons, such as programmers' mistakes or semantic inconsistencies between modules and so on. So one of the most fundamental things to achieve a cyber secure world is to provide better programming systems than the conventional ones. I would say that the next generation programming systems should significantly improve the quality of software by helping developers make safe software with simple and smart way. Then how do we achieve this? So from this lecture, from today, we will focus on three main emerging research areas. First is to achieve more advanced program analysis systems. The question here is how to overcome fundamental limitations of conventional program analysis that you have learned. The second one is security-oriented program transformation. How do we automatically transform the original program to make it more secure? Okay. The last thing is automatic program synthesis. How do we automatically generate a correct program that satisfies a given specification? Okay. All the approaches are commonly based on principled programming language theories and effective AI techniques. Okay. Among them, today we will talk about the program analysis part. As you already observed through the homework, the fundamental challenge of static analysis is to reduce false results, such as false positives or false negatives. Suppose this blue star represents a set of program states of your program, okay? And this red one represents a set of error states. Okay? Here, what we want to do is to check whether this program has an error state or not. Okay? But as you know, sometimes there exists some false positives because of coarse abstraction. Okay, that introduces this kind of spurious warnings. Okay, in practice, the dual problem can also happen if the approximation is tight but not conservative, okay, like this. Then what happened? It can miss some real bugs. Okay, this means false negatives, missed bug. Right. So in practice, reducing both false positives and negatives at the same time is really a difficult problem. Right. That is why many software analysis tools cannot find heartbleed bug, especially for a long time. This is a report from the world's largest software analysis company, Coverity. Okay. This says that it is really hard to achieve very low false positives and false negatives without sacrificing the scalability. Right? It's a really important but very difficult problem. Okay, then let's see how the conventional program analysis are usually designed. Conventional approaches have these kind of limitations because they are usually based on purely logical reasonings with highly hand-engineered heuristics. That is why a traditional static analysis system falls into either a bug finder that is in general very scalable but not very accurate, or a verifier that is in general very accurate but not that scalable. Okay, and we cannot achieve both in a single analyzer in a conventional way. So we hope that the next generation static analysis system achieve this part, right? Scalability and accuracy, right? How do we achieve that? Let's first take a look at the problems of conventional program analysis. Basically, it takes a program, okay, and produce a set of alarms to the user. Okay, that is a common workflow. The first problem, I would say that conventional program analysis is inflexible. It just follows the designer's choice, okay, designer's decisions, and hardly change its strategies once it is deployed. Okay, so here my point is that the analysis, okay, the analyzer needs to be adaptive. Okay. Second, there is no way to incorporate users' feedback to the output of program analysis system. Okay. It needs to be interactive. Finally, it does not fully take advantage of useful information other than a given target program. Okay? And it completely ignores old versions of the program or previous analysis result and so on. Okay? That means the analysis should be continuous so that it should exploit the previous information as well. Okay? So I strongly believe that these properties, okay, adaptive, interactive, and continuous analysis can significantly improve the state of the art and achieve the new analysis systems. Okay, and these properties can be achieved by combining these logical reasonings with probabilistic reasoning with AI. Okay. So here is the outline of this lecture. In this lecture, we will see three different approaches to solve each problem with probabilistic reasoning. Okay, so adaptive program analysis, okay, and interactive and continuous program analysis. So first, let's take a look at this adaptive program analysis, which is based on the following work. So program analyzers usually have a number of knobs, so-called sensitivities, okay, that control the degree of abstraction so that the behavior of analyzer will change accordingly. But if it has a fixed lower sensitivity, okay, for example, context insensitivity or flow insensitivity, which means very coarse abstraction, okay, then what happens? It would have very low cost, okay, in terms of time and memory, but very poor accuracy. Okay. Instead, if the analyzer is fixed with a very high sensitivity, which means too sophisticated abstraction, then it may run out of resource such as time or memory. Okay. Then the ideal solution is to design adaptive program analysis that automatically adjusts program analyzer's behavior by changing this knob, okay, depending on the environment, such as characteristics of the input program or the analysis progress or resource budget and so on. Okay. This general concept can be applicable to a variety kinds of knobs and costs with different learning methodologies. Okay. Here, the problem is that how precisely should we analyze the input program at risk of a certain cost? For example, how to construct a set of variables whose relationships are computed using relational analysis. Okay, that is the degree of relational analysis. Okay, in this case, the cost will be the running time. Okay, or the degree of flow sensitivity, which means the order of each statement, it can be also controllable. In this case, also the cost is running time. Okay, or the degree of unsoundness, okay, can be controllable. In this case, the cost can be, okay, the number of missed bugs, okay, and so on. So such adaptive strategies can be learned from old data, okay, using well-known learning methods, like supervised, okay, or reinforcement learnings, and so on. Okay. Here today, let's talk about one particular example, which is resource-aware program analysis. So here, our goal is to achieve the maximum precision within a given resource budget, such as within 128 gigabyte of memory and so on, okay, without fundamentally changing the underlying design of program analyzer. The key idea is like this, okay. So instead of running the analyzer with a fixed lower sensitivity, which would result in very poor precision, okay, or a fixed high sensitivity, which would run out of resource budget. Okay. This approach starts with a high sensitivity setting and keeps adjusting the strategy online by observing the environment, okay, such as resource usage, intermediate result, and analysis progress, and so on. Okay. More concretely, such a strategy changes a knob of program analyzer online. Okay. Here is an example of such a knob, flow sensitivity. Let's recall what flow sensitivity means. For example, flow sensitive analysis preserves all the order of statements and compute different information for each program point. Okay, as you can see, right? The other extreme is flow insensitive analysis that completely abstract the order of statements and compute a single program state which is valid for all program points, as you can see. Okay, for example, at any program point of this program, x and y can be either 0 or 1. Okay. Of course, there is something in between. We can control the degree of abstraction by choosing a subset of variables. Okay. In this case, we only apply flow sensitive analysis to variable x here and analyze, okay, the semantics of variable y in a flow insensitive way. Okay. So I will start with an example. Here is one program which contains 3 assertions. Here the goal is to prove these assertions as many as possible with the partially flow sensitive interval analysis, okay, within a given resource budget. Okay. For simplicity, here I just assume that the budget is given in terms of the number of intervals, okay, but the actual system works with physical memory budget, such as 128 gigabyte or 64 gigabytes of memory. So let's first take a look at how the flow sensitive analysis works. Okay. After the first line, we will have this abstract state that contains 3, okay, intervals. Here, for simplicity, we assume that top is not counted as an interval. Okay. And then after the second line, we have 2 abstract memories, okay, for line 1 and 2, right? And overall, we have 6 intervals now. Okay. If the analysis, okay, proceeds to the end, okay, then it will ideally prove query 1 and 2, as you can see, x and y, okay, the values of x and y are larger than 0. Okay, so ideally we can prove this query 1 and 2, but in practice it will actually learn out of resource. Okay, as you can see, we have 12 intervals. Okay. How about flow insensitive analysis? It will definitely fit in the resource limit, okay, but as you can see, it is not precise enough to prove the first query. Okay. Then how can we design an adaptive program analysis system that maximize the precision without violating the given resource constraint? Here is a simple system architecture. The analyzer takes an input program and eventually will output the result. Okay? But unlike the conventional approach, this solution is to learn a controller from data that changes abstraction during the analysis. Okay? Which means this system regularly trigger a learned controller, this guy, okay, that observes the current status, okay, and then tune the knob with respect to a given off-the-shelf statistical model of the particular abstraction. This one.